So in this video, we're going to look at problem 2 from the homework, which is another problem employing the method of joints in order to determine the forces in members within a larger than our previous problem, but still small truss. The main reason that I wanted to go over this, even though the technique is largely the same, is to show you how when you're applying method of joints, since you're approaching the equilibrium analysis of each joint as a statics of particles problem, that you can use forced triangles if you want. However, you have to be a bit intuitive in how you relax your assumptions about whether the members are in tension or compression. And I'll tell you what I mean by that in a minute. So we have a truss. It's subjected to one external load, a downward force P applied at point D. You're given the magnitude of P, and you're asked to basically solve for the force in each member and determine whether or not it is in tension or compression. So whether you're solving trusses by method of joints or method of sections, typically the first step is going to be to determine the external reactions that are supporting the truss as a whole. So kind of analyzing it using rigid body equilibrium analysis. So that's what I've done here. I've separated the entire truss from the points of connection at A and D. Since D is a roller connection, the reaction can only act perpendicular to the roller, so it is purely in the x direction, versus the pin connection at A could oppose forces both in the horizontal and vertical directions, so there are two unknowns associated with this. In terms of how you can go about determining each of these individual reactions, the first thing that you'll note is since only reaction A can supply a vertical reaction force, it has to offset that external load of 480 pounds. So if you sum all forces in the y direction, the math shows you that AY has to be equal to P, which is to say that as P pulls the entire truss down, that pin connection at AY pulls it up by the same amount. So that is 480 pounds. Now, in terms of determining the other reactions, we've accounted for AY. We want to show basically what you might see intuitively, that AX and DX are both 0. The way we can formally show that is to sum all moments about point A. That will isolate the only contribution to that calculation will be dx. Now, you might ask why that is. Well, notice that both AX and AY, they have points of application directly at A. So whenever a force is applied at a point, it doesn't contribute a moment about that point. But also remember that if the line of action of a force passes through a point, it doesn't contribute a moment either. And if you extend the line of action of this force P upward vertically, you notice that it actually passes through joint A. So none of these three forces, 1, 2, or 3, will contribute a moment about A. So what that means is when you sum all moments about A and they have to be 0, that's going to imply that dx has to be 0. You can write the expression for the moment if you want. If you notice, this has a horizontal line of action, so the perpendicular distance from the joint A is going to be 18 feet. So it'll be, in addition, if you pin at A and kind of rotate in the direction of dx, you'll see that that is a counterclockwise rotation. So by sign convention, it will be positive. So 18 times dx, well, it still has to be 0. The only way that's true is if dx equals 0. How can you show that ax is 0 now? Well, if you sum all forces in the x direction, ax plus dx have to be equal and opposite. They have to add to 0. So if dx is 0, ax is 0. Now, that's not to say that those reactions would be 0 in every circumstance. However, for the current loading profile, where you only have a force applied at D, that is what you're going to get. Now, how would you go about now knowing those external reactions, actually solving for the force in the members using the force triangle approach that I showed? So let's actually start and apply the method of joints at A. Notice that A has two members connected to it, member kind of AE, and then member AB. I think I might have called it AC in my free body diagram, but that's okay. That is a long member that extends all the way along the line of action of AC and AE. So remember that when we worked the first problem in the homework, we used what we referred to as compression assumptions, which means that the members pushed in on the joints, so the joints pushed out on the member. And therefore, when we assume that sense, if we get a positive quantity, that would mean that all members are in compression. So what if we didn't want to use the actual traditional decomposition and solving two simultaneous equations approaches that we used in the prior homework, but rather we wanted to use a force triangle? You can kind of see if you just drop FAB down that you're going to have a closed triangle. But remember back to the first chapter that we covered in the course, if you want to use kind of this method of polygons approach to equilibrium, all of the vectors have to be aligned in a tip-to-tail fashion. And if you swap this down here, right, you're not going to have that tip-to-tail based alignment because you're going to have the tail of FAB along with the tail of FAC. So if you were to drop this down and then you were to change the sense of FAC, you would have a closed triangle, as you see here. From the actual joint at A, you would have FAC going in the downward right direction, FAB pulling you back to the left, and then FAY pulling you up, and you would have a closed triangle that followed or satisfied the tip to tail convention in each case. So we can just attempt to solve for the two unknown forces, which are the forces in the members, FAC and FAB, using this force triangle. So the question is, how can we go about doing that? We've talked about law of sines, we've talked about law of cosines, but oftentimes when you're using force triangles, the easiest way to do it is just to use a similar triangle proportionality side length approach. So the question is, if we were to look at the actual geometry of this truss, we notice that FAC, right, it goes along going back to the original diagram here. If you look at FAC and you drew a triangle from E to A, and then you dropped it down to D, and you drew it all the way over to E, we would see that the geometry that defines the orientation of this truss is a triangle with a horizontal base length of 7.5 and a vertical base length of 18. So if we were to use Pythagorean's theorem, and I kind of drew the right side of the triangle, but you could draw the left side as well. But if you use Pythagorean's theorem to determine that hypotenuse, take the square root of 18 squared plus 7.5 squared, you get 19.5 squared. And then basically what we can say is that, and I should have, again, drawn the other side of this triangle. Maybe I'll edit this before I actually post it. But you can basically say that these two triangles are similar, the force triangle and the geometrical triangle. So the ratio of the force to the physical side length has to be proportional. So I can take FAC, the unknown magnitude of the force, to the actual length of the hypotenuse in the force triangle, which is 19.5. So FAC to 19.5 is proportional to FAB, which is this base horizontal length, to 7.5, which is the, FAB is the base horizontal force. The base horizontal length is 7.5, so those ratios are proportional to the ratios of the vertical force to the vertical displacement as well. So from this, since you know AY, you can iteratively solve first for FAB and then FAC. It doesn't matter, you can do it in the other order as well. But the key point is if you apply the force triangle approach, you're really doing making the force triangle proportional to the underlying geometry in the truss. The one thing you want to be careful of is you've changed your underlying assumptions. When we did problem one within this homework, and we assumed that all forces were pushing in on the joint, those are compression assumptions. Now we notice that since we changed the orientation of FAC, whatever number you get here, note that it's pulling out on the actual joint, which means the joint is pulling it back in. So FAC now, since it's going away from the joint, that quantity when it's positive will be in compression. FAB, that quantity, and it will be positive because of the technique we're using, is still in compression. So just be careful that you have to think a little bit about the nature of the signs that you get as part of your results.